So hello everyone, my name is June. I'm moderating the session on federated learning and machine learning. And so welcome to the event. And this is the Connect session where we are trying to kind of improve upon the current model of cross-researcher interactions, right? Which is only happening nowadays within conferences. But now we are trying to make this happen in your room through virtual spaces on a bi-weekly basis, like in this session. So the goal is to make people know each other in the same field, like federated machine learning, and have some discussions. It's happening every 2 weeks. And the format is we have 10 minutes for the presentation for each speaker. But now, since you're alone, maybe you can use a little bit more time, of course. We have discussion at the end after the session. The recording is being done now. So after the recording, we put the video on YouTube. And of course, the speaker has full freedom to say no to this afterwards. So you can opt out at any time. So let's probably get started with the presentation.
Okay.
I'll stop sharing.
Okay. I will share from my side.
Yes.
Can you see my screen?
Yes, I can see your screen.
Yeah, okay. Hello, everyone. My name is Xiao. I'm the 4-year PhD student and also the final year PhD student in TU Eindhoven data mining group. And thanks for coming to today's presentation and thanks for the invitation from Zoom. In today's presentation, I will briefly to introduce one of our recent work addressing the collaboration dilemmas in low data fidelity learning via transient sparsity. This work we cooperate with the University of Luxembourg and the University of Twente in Netherlands. Let us start the presentation. In the beginning of this presentation, I will briefly to introduce the fidelity learning. Fidelity learning is the machine learning setting with multiple clients collaboration to solve the objective problems under the coordination of the central servers. So based on this training paradigm, there are some advantage. First of all, it can preserve the data privacy. It's quite critical for some sensitive domains like the healthcare, financial data, and these kinds of the sensitive domain. And also it can leverage the diverse knowledge from the multiple sources because we can learn the knowledge from different clients from the model perspective. But there are also some challenges in this training paradigms. Like we don't have too much data to train the model very well in each client. So it can lead to some risk of the local model overfitting problem. So in this work, our purpose is to solve based on this challenge. When we train the fidelity learning in the low data scenarios, we found some phenomena in the layer-wise learning dynamic. Here is about the layer-wise inertial phenomena we observe in these cases. What is the layer-wise inertial phenomena? We observe the middle layer of the global model undergo minimal updates after early loss of the communication. This is evidenced by the quite high layer-wise similarities in the global model between the early and the later training stage. Here we define the layer-wise cosine similarity in L layer between the T loud to TO loud, and we observe quite pretty high cosine similarity, especially in the middle layer. And why this happens? This is because of the overfitting programs. It reduced the vulnerabilities in local updates. We have some result here. We train the models under different training data set with different architecture. We can see that most most of the middle layer we observe quite pretty high layer-wise cosine similarity, and this means that the middle layer don't have too much update or change during the trainings after the early of the training early of the communication, the loud communication. So this is something like the lazy updates in these cases. We also observed that even though we change the data distribution in the clients, this phenomenon didn't change too much. So in other words, the data distribution in the clients cannot adjust the these kinds of the phenomenons. And so based on this observation, we also found that it has some negative impact to the aggregations. It made the aggregation become less effective. Here we have some experiments. Given a models, we can given a training cases, we only aggregate in the early of the trainings. After that, we don't have the aggregation anymore. We maintain the local trainings, and we compare with the one of the training cases. We do the aggregation every round. We found that the difference between their performance is quite margin. So it means that the aggregations after a certain round of the communication, they don't have they are useless. They don't have any benefits in these cases. So this is quite challenge in the fidelity learning cases. So how we can solve this problems? Here we propose to use the methods to stimulate more meaningful updates in the more meaningful updates. So here we use the methods like the sparsity here. Why we use the sparsity? Because sparsity is the kind of method to reduce the overfitting problem. In our cases, we would like to disrupt the model's reliance on the weights caused by the overfittings. So we if we would like to do this based on the sparsity, so how we can identify the weights caused by the overfitting? Here we propose a criteria termed as the sensitivities criteria. This based on these criteria, we can identify the ways we would like to specify. So the metrics can be defined as the gradients multiples the weight values. So with lower sensitivities, we can we can zero out these parameters and then to make the model in the next training step to activate again. So after we identify these parameters, we can apply the mask to the global model, and then the local clients can, based on this masking global models to continue to train the local for the local training. To evaluate our models methods, and we test on 3 kinds of the data set using 3 different model architecture, and we also evaluate on the different sample size in each client, and also evaluates when scaling the number of the clients. And we also have some evaluations on the different data distributions, we can see the overall results under the different data sets and different data distribution. Our proposed method can consistently outperform the baseline. We also have some scalability analysis. We scale up the client's number, and also we scale up the data size in each client. We can observe that, especially under the more number of the clients, and also under the low data size in each client, we can have the better performance. And also we have some abrasion study to evaluate our proposed sensitivities criterions. We can find that in general, in most cases, the proposed methods sensitivities criterions can have the better performance compared with the others selection, the parameter selection metric. And finally, we also have some visualizations on the layer-wise learning dynamic. After we apply the proposed methods, we can see that compared with the layer-wise cosine similarities in the beginning of the presentation, we can see that we can observe the quite lower cosine similarity for all layers. In this this means that the layer, especially the middle layer of the model, has already get more meaningful updates compared with the previous methods. And we also observe some higher gradient norms compared with the baseline methods after applying our proposed method. I think this is the main reason why it can have more meaningful update, because the gradient norm already increase a lot compared with the original one. And finally, we have some conclusion and some discussion on some future work. We firstly to identify the layer-wise inertial phenomenon in low data federated learning scenario. And based on this observation, we propose some simple but quite effective solution by using the sparsity methods. And we demonstrate the improvement across diverse federated scenarios. For the future work, I think it's quite interesting to explore the sparsity scheduling methods to allocate the layer-wise sparsity and for the different data set and different architecture. And also, I think it's quite interesting to explore on the larger model like the transformer-based model, and also the more complex task. And that's all from my side for today's talk. If there are any questions, we can discuss, and also you can send me the email if you have further questions.